This is a short presentation on nonmetal elements. Nonmetals are located in the upper left-hand corner of the periodic table. They include both kind of typical nonmetals and also our noble gases. So up in that upper left-hand corner of the periodic table, based on our periodic trends, these all have high electronegativities, high ionization energies, large effective nuclear charges, and small sizes. And this really leads to a lot of their properties. I'm going to call out the second period of the periodic table in particular, our second row. This is carbon, nitrogen, oxygen, and fluorine. And focusing on these elements, they are special. They do not have any d orbitals in them at all, and they are extremely small. They're our smallest elements on the periodic table. And because of these two things, they get extremely good overlap between orbitals when you bring these elements together. And so they have a much greater ability and affinity for forming pi bonds. They're just better at it. And that's why we see so many double bond or triple bond structures to these elements. It also helps make them really strong oxidizing agents. And actually, what makes all nonmetals good oxidizing agents is the fact that they have so many different oxidation states available to them. This goes beyond that second row of elements. Most or nonmetals will oxidize most metals. And so they participate in a lot of redox reactions. Of our nonmetals, fluorine and oxygen are our strongest oxidizers. In fact, they're some of the strongest oxidizing elements, period. Nonmetals also form really fascinating structures that go beyond the typical monoatomic atom in the elemental state. Now, our nonmetals do that. They all form monoatomic elements because they have a filled set of electrons in their valence shell, and they don't have any incentive to bond or react. And so they're very non-reactive. Now, the rest of our nonmetals, they all form diatomic molecules in the elemental state, where they're covalently bonded. And beyond that, many of our elements actually form different elemental structures that in addition to that diatomic state. We call these allotropes, where the arrangement of atoms actually gives that element a different set of physical properties than another elemental version of it. So starting with carbon, carbon has lots of allotropes. Think about diamond, graphite, charcoal, coke. Carbon black itself can be graphene or fullerene. It can be structured as nanotubes. I have a picture of graphene here for my carbon allotrope, and it has a conjugated single double bond system, coming back to that incentive to form strong pi bonds because they're such a small atom without d electron orbitals. And the graphene, they can actually conduct electricity with these conjugated bond pi systems that have lots of resonance structures and delocalize electrons over the material. Oxygen has allotropes of O2 and O3, ozone. Phosphorus has 3 allotropes. The most interesting to me is P4. P4 is white phosphorus. It bursts into flames and gives off a very bright white light that's used in firework making. Now, if you take those P4 structures and network them together with covalent bonds, you'll have red phosphorus, and it's less reactive. Sulfur has our most allotropes of our nonmetals. And within its many allotropes, I think S8 is the most interesting. It's 8 sulfur atoms covalently bonded together. And how those 8 atoms arrange themselves relative to one another changes its properties. If they take on a rhombic configuration, you'll have the most common form of sulfur, which is this like yellow powdery sulfur. But if they arrange themselves in a monoclinic fashion, you're going to get these long spindly needles of sulfur instead.